Okay, let's take a look at some electron configurations here. You've walked through electron configurations. They're a collection of elements that are up here, and those are highlighted so that we can take a look at how do we do the electron configuration and just remind ourselves how to do that. So we'll start with some easy ones, and then we'll go to some ones that are a little more interesting. So if I start with magnesium, as much as possible, I'd encourage you to do the shorthand method. So that means we're going to pick the noble gas in the row above our element, so in this case it's neon, and we're going to put it in brackets. That's the kernel. That is the full energy level. And then we're going to take a look at the row our element is in. Magnesium's in the third row. So that means that we're going to start out with a 3, and then it's in the S block, and it has 2 s electrons, so it's 3s2. We take a look at arsenic. Arsenic is in the 4th row. So the element that will be in the kernel, or that has completely filled orbitals, is this time going to be argon. Because arsenic is in the 4th row, we're going to start with our 4th energy shell. And as we move left to right, we have the S block, the D block, the P block. And electrons are put in order. So we're going to put s electrons in first, and that's filled, so that's 4s2. Then we move to the next block, which is the D block. The D number is always 1 smaller than the S number. So we have 3D, and we've gone all the way through the D block, so that's filled, and we have 10 D electrons. P number and S number are the same. They're the valence electrons, so we have 4P, and arsenic is the 3rd element over, so we have 4P3. Now that P orbital is half-filled in arsenic. The half-filled condition, remember, is relatively stable. Completely filled orbitals are very stable. Half-filled orbitals are pretty darn stable. So arsenic is a relatively stable compound. Take a look at some more interesting elements. Let's take a look at chromium. Chromium is in the 4th row, so we're going to use argon as our kernel. 4s. Chromium is the 4th element in the D block. So we would initially think it should be 4s2 because it's beyond the s orbital, and then 3d, and we count over 1, 2, 3, 4, so 3d4. But the elements in this column are almost stable. We almost have a half-filled d orbital. So what this element does, and the ones below it, because the s orbital and the d orbitals are so close in energy, we're going to make it a more stable configuration by moving one of those s electrons up into the d block. So what we get is the argon shell, 4s1, and so one of those s electrons becomes now a d electron, and we have 3d5. So our s orbital is half-filled, our d orbital is half-filled, and we have a very stable electron configuration for chromium. And so this is the accepted electron configuration for chromium. Giving the original one will not get you full credit if you're asked to give an electron configuration for that element or elements also in that group. Same idea with silver. Silver's in the same row. No, silver's in row 5. So we're going to go to row 4. Krypton is in our kernel. So we have 5s1, 4d9. If we originally follow the plan and fill electrons from lowest to highest energy level. Oops, 5s2, 4d9. But again, d9 is almost full. And so this isn't a very stable electron configuration, so silver, like chromium, is going to borrow an s electron to have a half-filled orbital and a completely filled orbital, which is much more stable. So the electron configuration for silver is krypton in the kernel, 5s1, or d10. And so this would be, again, the accepted correct electron configuration for silver rather than the first one that we wrote. The elements in that column, so copper and gold, behave exactly the same way. What that tells us for silver and gold, but not so much for copper, is when electrons are lost to form positive ions, transition metals always lose their s electrons first. So silver and gold, losing an s electron, are going to be +1 ions rather than +2 ions. Copper loses its s electron, and it also loses that d electron that it borrowed. So actually copper is a +2 ion that's much more stable. And if we wanted to talk about the whys and wherefores, we'd have to go to some upper level chemistry. And we're not ready to do that, so we'll take a look at some other elements here. Let's look at tantalum, Ta. Tantalum is in row 6, It's element 73, so we're going to put xenon in the kernel. 6s2, because that's where we start now. If we start counting over from left to right, we'll see we go from element 56 barium, and then there's this gap. And that gap is the lanthanide series, which is all the F block elements. And so we need to put those in. And again, we tend to, when we write electron configurations, write them down in the order in which the electrons were put in. So we go from S to F. The F block is 2 smaller than S, so we have 4F. And we go all the way through the F block, and there are 14 elements there, so it's 4F14. And then we go to the D block. D block again is 1 smaller than S, so we have 5D. And tantalum is element 1, 2, 3 over, so it's 5D3. And so there's our electron configuration for tantalum. The last element we're going to take a look at is promethium, element 61. Promethium is also in row 6, so we're going to have xenon again as our kernel, so 6s2, 4f. All right, if we count over, we have 1, 2, 3, 4, 5, 4f5. So there we are with our electron configuration for promethium. You should be able to do electron configurations really for any element in the periodic table, and the patterns are for the most part basic. You probably wouldn't be asked to do really challenging ones, but these are not considered really challenging, so these are ones you should be able to do.